Hello, everyone. I am Jenny Oakley, and I'm the Associate Director of Research Programs at the Environmental Institute of Houston and adjunct faculty of the University of Houston Clear Lake. So I'm not presenting to you live today, but I've provided my email address here in case you have any questions or want to reach out to me regarding this talk on aquatics. Now, I'm probably a little biased, but aquatics is the most important of the subjects in Envirothon. Understanding aquatics is central to all ecosystems, all habitats, all critters on our blue planet. And they call it the blue planet because it's 75% water. Of that, most is salt water, but of the fresh water, most is in glaciers and ice sheets, at least for now. In fact, did you know that water makes up about 60% of the average human's body mass? Water, or the compound H2O, is what makes life on Earth possible. First, it's a universal solvent because it's able to dissolve more substances than any other liquid. Now, this is extremely important for living things and why water is such an important part of our human bodies. But the fact that water is a great solvent also makes it extra difficult to manage when we're looking at pollutants, and we'll talk about this later. Water also has high surface tension, so many animals have evolved to take advantage of that, if you think of the water strider. And water also has a neutral pH and naturally exists in all three states, so that's liquid, solid, and gas. The water cycle, that's also known as the hydrologic cycle or the hydrological cycle, is a rather complex process that describes the continuous movement of water on Earth. Water is kind of like energy, neither created nor destroyed. In fact, it has stayed fairly constant over Earth's history. However, the partitioning of water can change drastically. So water in all of its states is cycled through the processes displayed in this diagram, the typical water cycle. The water cycle directly impacts temperature, weather, and climate on Earth, and many of the processes in the water cycle also can naturally purify water. So water pollution comes in many forms, but as I briefly mentioned, the very properties of water itself makes it such effective at spreading pollution throughout the environment, and in terms of aquatic critters, it makes that pollution more impactful to them. So here's a quick history of measures to protect water quality in the United States. The history of the Clean Waters Act goes back to 1899 and even earlier with the Rivers and Harbors Act and subsequent Oil Pollution Act of 1924. But the first real major implications for surface water quality was in the Water Pollution Control Act of 1948. So this act had many amendments, and some of the most important were the 1956 amendment and the 1965 amendment, which renamed the act. And the intention of the development of standards for water quality were really defined in these acts. However, there was a regulatory understanding for the need to protect water, but for many citizens, they were kind of removed from some of the major issues that were surrounding water impairments throughout the U.S. Then in 1969, the Cuyahoga River near Cleveland, Ohio, caught on fire. Now, this is not the first time the river burned. At least 13 fires have been reported on the river, first occurring in 1868. But what made this time different was that Time magazine did a piece on the fire, and they used photos from the 1952 fire, which really opened the eyes of many readers across the country that we have some major water quality issues that need to be addressed in the U.S. So publicity demanded stronger action, and just 1 year later, the Clean Water Act established the basic structure in use today for regulating pollutant discharges into waters of the U.S. and setting water quality standards for surface waters. So control programs such as the construction of wastewater treatment plants and point source permits and dredge material, that was all really developed and put into place with the 1970 Clean Water Act. So in terms of water, there are really kind of two categories or sources of pollution, and that's point source and non-point source pollution. Point source pollution enters the water at a single identifiable and discrete point. So think about like a pipe or a conduit, like a drain pipe from an animal feedlot or a power plant discharge. And non-point source pollution enters water without a single identifiable or discrete point of entry. So this is like overland runoff from agricultural lands, like fertilizers, pesticides, herbicides, and urban runoff from like oil and grease, from the roadways. All of this enters the stream through stormwater runoff. There are two types of water that are in liquid form other than oceans, and that's groundwater and surface water. So if you remember back to our water cycle, when rain falls, it seeps into the earth, and that's called infiltration. And it fills the cracks and crevices and pores and spaces of an aquifer, which is basically an underground storehouse of water, and it becomes groundwater. So nearly 40% of Americans rely on groundwater that's pumped to the Earth's surface through wells or other devices for drinking water. Groundwater gets polluted when contaminants from pesticides and fertilizers or different waste is leached from landfills or septic tanks, and it makes its way into the aquifer. So groundwater can also spread contamination far from the original polluting source as it seeps into streams and lakes and oceans. Furthermore, the overuse of groundwater can cause the water table in the aquifer to fall. And in some systems, it can cause the surface water to fill that void, causing reduced flow in surface water systems. Here in Texas, the agency that's charged with monitoring water quality is the Texas Commission on Environmental Quality, or TCEQ. And they have a surface water quality monitoring, or SWCM, team that works to, and I quote, establish explicit goals for the quality of streams, rivers, lakes, and bays throughout the state. The standards are developed to maintain the quality of surface waters in Texas so that it supports public health and enjoyment and protects aquatic life consistent with the sustainable economic development of the state. So water quality standards identify the appropriate use for the state's surface waters, and this includes aquatic life and human use. So for example, recreation and sources of public water supply or drinking water for humans. The criteria for evaluating the support of those uses includes dissolved oxygen, temperature, pH, dissolved minerals, toxic substances, and bacteria. So we're going to talk a little bit more about those. For aquatic life, the goal is that the surface water of the state is able to support diverse and healthy communities of aquatic critters. And so those critters include fish, invertebrates, plankton, and plants like pyraphyton. So these are some examples of typical criteria measured to determine if surface waters meet standards set for human contact or aquatic life use. Many times scientists use something called a multi-parameter sonde. Picture is on the top right of one of those sondes. And they're used to measure things like temperature, dissolved oxygen, pH, specific conductivity, and even things like chlorophyll levels in the water. They can also use something called a Secchi disc to measure the water clarity. And there's also different methods that are used to measure flow or discharge when dealing with flowing water. So if a team is working in a flowing water system, like a river or a stream, discharge is really key to understand the water quality and, more importantly, loading of pollutants in the system. Discharge is the amount of water that flows through a specific area in a specific time. It's often represented as cubic feet per second. So dissolved oxygen is the leading cause of fish kills in Texas, or rather the lack of dissolved oxygen is the leading cause for fish kills in Texas. Dissolved oxygen, or DO, naturally fluctuates with temperature and time of the day. The warmer the water temperature, the lower the capacity for the water to hold dissolved oxygen. So this, along with other factors, including decreased flow due to less rainfall, are why we tend to see the lowest dissolved oxygen levels in the summer in Texas. There's also daily fluctuations in dissolved oxygen. So, for example, if I were monitoring 24 hours of dissolved oxygen in a river, I would expect to see the highest DO levels just before the end of the day, and the lowest DO levels just before sunrise. So now this makes sense if you think about the fact that much of the DO in these freshwater systems comes as a byproduct of photosynthesis from plants and algae. So all day long, as the sun is shining and it's out, DO is being added to the water by plants. And at night, that source of DO stops, but the respiration that's happening from all the critters that live in the stream continues, and it uses up the DO that's available in the water column. And with no photosynthesis to resupply it until the morning, when the sun comes out again, it tends to get lower and lower and lower and lower throughout the night. And then as soon as the sun comes up, we start reproduction of dissolved oxygen in the water, and it starts to rise again. Oftentimes, low dissolved oxygen is caused by something called eutrophication. And this is when there are excess nutrients. So if you think about fertilizers that are washed into streams and rivers from non-point sources, these excess nutrients are food for bacteria and algae, which can multiply in great numbers. And when there's plenty of food nutrients available, they can reach really large numbers, but eventually they'll die off. And that creates an influx of material that needs to be decomposed. And the process of decomposing burns through dissolved oxygen, and that causes there to be too little oxygen in the water for critters like fish or clams to breathe, and this is called hypoxia. So another metric for measuring water quality can be things like heavy metals. Metals such as arsenic or mercury or lead tend to bioaccumulate, and this means that they are rarely processed in the digestion of aquatic critters, so they accumulate in their bodies. And then those pollutant loads can be transferred to the predator that consumes them, causing our top-level predators to have sometimes very high levels of these heavy metals and other bioaccumulating pollutants, which can have health impacts to those top predators. Now, as I mentioned earlier, in Texas, the Texas Commission on Environmental Quality is charged with monitoring the quality of surface water in the state. So this is mostly done through the Clean Rivers Program, or CRP, which is a consortium of agencies, organizations, NGOs, and academic institutions that regularly monitor water quality. In our area, Houston area, the organization that acts as the kind of group leader for the Clean Rivers Program is the Houston Galveston Area Council. And so they corral the 6 regional partners and over 370 monitoring sites that make sure that the monitoring data are submitted to the TCEQ and all quality controlled, and that we are continuously monitoring the quality of the surface waters of the state and our region. So this map shows all of the monitoring sites in the Houston area. From monitoring all of those sites, there's some things that we can discern about the water quality in this area. So out of all of the parameters that are monitored, bacteria is one of the most significant water quality issues that we have in the Houston area. Bacteria concentrations are monitored to determine if the water body is safe for recreation, and the bacteria that are tested are enero for tidal waters and E. coli for fresh waters. So these are pathogen indicator bacteria, meaning typically when we see really high enero or E. coli levels, we also see higher levels of other pathogenic bacteria, viruses, or protozoans. So 42% of stream miles that we monitor in our region are impaired from elevated bacteria levels. In the map on the right there, the blue lines are the stream segments that meet water quality standards. The yellow and red lines exceed the standards, with the red lines having more extreme exceedances. Sources of bacterial contamination include untreated wastewater from treatment facility releases or sanitary sewer overflows, failing on-site sewage facilities or septic systems, and fecal waste from livestock, pets, hogs, or other types of wildlife. Another parameter that's monitored is dissolved oxygen, and I already mentioned that DO is the most common cause of fish kills in Texas. It's measured to determine if a water body can support aquatic life. So DO levels can be negatively impacted by human actions like high concentration of nutrients from agricultural runoff, which can cause algal blooms and then can temporarily increase dissolved oxygen, but typically results in crashes in DO after the die-off, like I mentioned before. So production of shade from natural riparian buffer along the water can result in really high temperatures in the water. And like I mentioned before, the warmer the water, the less dissolved oxygen that it can hold compared to cooler water. Nutrients, including phosphorus and nitrogen, naturally occur in surface waters. However, human activities can cause excess nutrients, which can in turn impact the water quality and cause algal blooms and depress dissolved oxygen, and produce even toxic, harmful algal blooms that are harmful to humans and wildlife. So 35% of stream miles in the Houston area exceed the state standards for nutrients such as nitrate, ammonia, and phosphorus. Some sources include runoff from both point and non-point sources, from fertilizers or animal manure, and excess nutrients from wastewater treatment facilities and on-site sewage facility failures. Finally, PCBs, or polychlorinated biphenyls, and dioxins are broad groups of synthetic organic compounds that are developed for industrial purposes, or they're byproducts from industrial processes. So they are toxic and carcinogenic and considered legacy pollutants. So they remain in the environment long after they're introduced. They also bioaccumulate or biomagnify, and 6% of freshwater streams, 60% of tidal streams, and 75% of bays in our area are impaired for PCBs and dioxins. So one way that scientists can evaluate a surface water body is to see what types of critters are living in it. So to do this, they go out and they collect as many aquatic fish or invertebrates as they can in their study area. So for example, the numbers and the types and life history of the fish caught in a segment of a stream can tell the scientists about the health of the water. So many aquatic fish or invertebrates are categorized into one of these three categories. Sensitive species are only found in very specific conditions, so typically indicative of very clean water, while other species, for example, the western mosquito fish, which I'm pretty sure you can find anywhere and everywhere, are considered tolerant species. The proportion of fish in the population that is made up of each of these kind of sensitivity types helps to score or rate the biological integrity of that water body. So in a stream where we would see kind of an even number of sensitive, intermediate, and tolerant species, we could say that that's probably a healthy system. Whereas a stream that we found mainly tolerant individuals and maybe a few intermediate individuals, that would be an indication that that stream has water quality issues. It's potentially polluted and it requires further investigation. So along with water quality and then the biotic community, there are also physical habitat characteristics that are indicative of a healthy surface water body. So for streams and rivers, a natural meandering pattern increases habitat diversity, and that in turn can increase species diversity. Also, an intact riparian zone, which is that kind of interface between the land and the water, so like the edges of a river or stream, can provide habitat, but it's also really important in stream shading, which can help regulate water temperature in the stream itself. There are signs of a degraded stream, including channelization, which can result in higher velocities during rain events that cause scouring and erosion. So that kind of blurry figure in the middle bottom of your screen shows a kind of natural stream, that green slope. From a rain event, you would see, increased flow, increased velocity, but it'd kind of ramp up slowly and then decrease really slowly. And then when you move into suburban, the yellow, and then really urbanized streams, the red, that same size of a rain event can cause a really steep and drastic increase in velocity and flow that falls off very quickly. And so anytime you have increased velocity, increased discharge like that in a really short period of time, it can cause scouring and erosion. Also, the artificial substrate that's usually used in these urban systems, like concrete, kind of creates streams that have really little habitat complexity, and that results in lower species diversity. There's not as many places for kind of niche fish to hang out and hide in. Also, the lack of riparian plants can cause higher water temperatures, which, as we mentioned before, can impact the dissolved oxygen. So along the coast, the fresh surface and groundwater meets the salt water of the Gulf of Mexico, and this area is kind of a mixing zone that occurs in the bays and estuaries and up into the tidal rivers and bayous and creeks along the coastal plain. And so this mixed fresh and salt water is called brackish water. So many times where there are two water masses that meet, there's something that one of them's fresh and one of them's salt. There's something that's called a salt wedge that happens. So salt water is heavier than fresh water because salt water has many more dissolved minerals in it. So when fresh water flows into salt water, the fresh water tends to kind of float on top of the salt water. And the salt water layer below is called a salt wedge. And it's typically kind of angled like that wedge shape. The wedge can move up and down the stream based on kind of freshwater inflows and the tides, but oftentimes there's really a distinct layering of the water here. It's called a halocline, and this can impact mixing, vertical mixing in the water column. It can impact dissolved oxygen and nutrient cycles in these really kind of dynamic brackish water systems. So the salt wedge also causes the flowing water, the fresh water that's flowing in, that flowing water mass to slow down, which allows the suspended sediments to kind of precipitate from the water column and fall out. And I'll explain why this is really kind of important in a minute, this sedimentation that happens right at this brackish water zone. So I've talked a lot about water quality, but another challenge water resource managers face is water quantity. So as climate change continues to create more extreme weather patterns, and we have sometimes excess waters in the form of floods, but also other times insufficient water in the form of droughts, we'll continue to have to manage the quantity of water that we have available to us. So in Texas, water from both surface and groundwater sources are used for irrigation and municipal systems, so our drinking water. In fact, irrigation accounts for 59% of the total water usage in Texas. Most of that's from groundwater. And the municipal use accounts for about 28% of total water use in Texas. So that's our drinking water and water that we use for, bathing and things like that. So Texas surface water is owned by the state, and it's held by the state in trust for the public. It is a public resource. So a water right is defined as a right that is acquired under the laws of Texas to impound, divert, or use state water. And the TCEQ, again, is the agency that manages and permits the use of water. Currently, if you add up all of the water rights that are approved in the state, during times of drought, there is a possibility that there would be not enough water for farmers to irrigate their crops or for people to drink, and certainly not enough to leave any surface water flowing into our bays and estuaries. So the concern for that in these future extreme droughts, where there would be insufficient water flowing into the bays to keep them healthy, prompted something called Senate Bills 2 and 3. In 2001, Senate Bill 2 directed 3 state agencies, the Texas Parks and Wildlife Department, TPWD, the Texas Commission on Environmental Quality, the TCEQ, and the Texas Water Development Board, the TWDB. So in cooperation with other agencies and groups, their job was to jointly establish and continuously maintain an in-stream flow data collection and evaluation program. So in addition, the legislature directed the agencies to conduct studies and analysis to determine the appropriate methodologies for determining flow conditions in the state rivers and streams that are necessary to support sound ecological environment. So the resulting program is known as the Texas Instream Flows Program, the TIFP. And the TIFP conducts detailed in-stream flow studies which consider a wide range of environmental variables such as habitat, hydrology, biology, physical process, water quality, connectivity. All of these things dictate kind of a multidisciplinary effort. So the goal of each of these is to identify appropriate flow regimes that conserve fish and wildlife resources while also providing sustained benefits for other human uses of water resources. So given their complexity, in-stream flow studies take many years to complete, and only a small portion of the state's rivers have been addressed to date. The TIFP studies for specific river basins will be conducted in a 4-step process that involves kind of public stakeholders and scientific peers, as well as multidisciplinary technical studies. So the process for in-stream flow studies is kind of shown in this flow chart on the left-hand side here. So far, 6 river subbasins have been identified as priority in-stream flow studies. These subbasins were selected based on potential water development projects and water rights permitting issues and other factors. But essentially, Senate Bill 2 and the Texas In-Stream Flows program manages sufficient water for healthy rivers and streams. Whereas Senate Bill 2 provides for detailed studies and determination that the in-stream flow needed for these priority river basins, the legislature did recognize the need for identifying appropriate amounts of water to set aside for the environment. So they passed Senate Bill 3 in 2007. So Senate Bill 3 is a stakeholder-driven process. It's designed to use existing information and the best available science to establish environmental flow recommendations and standards for the major Texas river basins and the estuaries that they flow into. The intent of Senate Bill 3 is to address three major questions. That is, number one, how much water is needed to sustain a sound ecological environment in the state's rivers and estuaries? Number two, how can this water be protected? And number three, what is the appropriate balance between water needed to sustain a sound ecological environment and water needed for human or other uses? So a pretty difficult task. Now, fresh water is needed for our bays to stay healthy. By regulating the salinity for some of the critters that specialize at living in kind of those low salinity habitats, low salinity waters. Fresh water is also needed to deliver nutrients that supports kind of the base of the food web for the bays, and also for delivering sediment. So this sediment delivery is a very important process, and it develops these kind of complex and dynamic river deltas. So this right here is a satellite image of the Trinity River Delta. So the sediment that's deposited into the deltas is critical, and it happens because of that kind of salt wedge process that I talked about earlier. And it's the way that our coastal areas naturally combat sea level rise along our coasts. So when the freshwater inflow is reduced, along with, of course, the sediment delivery that naturally occurs, the sediment buildup along our coastal areas is reduced. So here along the Gulf Coast, and maybe you've heard of this number before, it's kind of crazy, we lose more than 1 football field of coastal land every hour. So now that kind of seems impossible, but with development, subsidence, the reduction in natural sedimentation from reduced freshwater inflows, and then sea level rise on top of all of that, that loss of coastal wetlands is really astonishing. I'll go back and show you that exact same aerial imagery again. So I am going to play an interview on a radio show called Living on Earth. And Bob Marshall explains the land loss in Louisiana, and he mentions a project called Losing Ground. So I'm going to navigate to the website that's posted here and explore it and follow along with Bob's interview. So kind of bear with me. The maps they contain a lot of data. So the first time I scroll through the time lapse, they can be a little jumpy. But after I do, I'll go back and forth a few times so you can really see the slide bar and the wetland change through time. So this is an example from Louisiana, but the same thing is happening along the coast of Texas. So I'm going to go ahead and play it now.
Louisiana is growing smaller and smaller thanks to changes in the Mississippi Delta that were designed to increase flood protection and enhance oil and gas production. Bob Marshall has been covering coastal land loss in Louisiana for decades. He's now a writer with The Lens, a nonprofit news site in New Orleans. He recently collaborated with ProPublica to put out a graphically enhanced report called Losing Ground. Complete with dynamic maps and images, Losing Ground shows just how much of Louisiana's wetlands have been eaten up by the Gulf of Mexico. Bob Marshall joins us now. Welcome to Living on Earth.
My pleasure to be here.
So the project is called Losing Ground. How significant is this land loss crisis? How quickly are we losing ground down in Louisiana?
Well, right now they're losing it at about 16 square miles a year. They like to say a football field every 48 minutes. But if you go back 20 or 30 years ago, we were losing as much as 50 square miles a year. So we've lost about 2,000 square miles since the mid-1930s, and there's very little left now in southeast Louisiana.
Now, I gather a lot of this has to do with the way people have controlled the Mississippi River over the years. Describe that process for me.
Well, this whole area of the state, all of South Louisiana really, from Mississippi to Texas, was built by the Mississippi River. Its delta building process going back about 7,000 years, when the end of the last glacier period. When the river hits this flat plain, it slows down, and all the sediment it's carrying begins to fall out. And it wasn't just the main stem of the river. It There was all these distributaries that peel off the river on its deltaic plain. So there was this big, really spider web of distributaries carrying all this fresh water and sediment. And during the spring floods, the river would come over its banks and over the distributaries' banks and spread this really nature's cement, if you want to call it that, out all across this area. And so that process was still going on when Europeans arrived, and when New Orleans was founded in 1718, they were still building land out into the Gulf of Mexico. And everything went along as nature intended it until we began developing along the river, and people began putting up levees so that they wouldn't get flooded by this river every spring.
So what did the levees do to the river exactly? Why did it make it lose land?
Well, the levees block the river from spreading more sediment out on its delta. And so when a river can't get back out to replenish its delta, that delta begins subsiding. So there were levees on the Mississippi really going back to the 1850s. But after the Great Flood of 1927, when most of the Mississippi River Valley from Illinois to Louisiana was flooded, Congress said, never let this happen again. And so the Corps built these great levees, and they put the river in a straitjacket, permanently blocking the river from getting back to its delta to replenishing this land. If that's all we had done, though, researchers say that the delta would have been subsiding at an infinitesimal rate, millimeters per year, and the wetlands that were intact in the 1930s when these levees were finished would still be largely intact today.
But that's not what happened, I gather.
That's not all we did, because at the same time we finished those levees, oil and gas was discovered in this coastal zone, and we proceeded to go after it because there were no protections for wetlands then. Eventually 50,000 wells were permitted in this coastal zone. Over 10,000 miles of canals were dredged for oil and gas, 500 miles for shipping, and we basically eviscerated this incredible delta. There have been dozens of reports that show where there was the heaviest amount of oil and gas extraction and canal dredging. We had the highest rate of land loss and subsidence. So we're fighting this massive loss of surface land. We're also subsiding, right, because we're not replenishing this land, these wetlands, I should say. And on top of that, here comes global warming and sea level rise. So we're in this precarious situation where we have, according to NOAA, the highest rate of relative sea level rise of any place in the country, and one of the highest rates anywhere on the planet. So where most of the country might be looking at 2 feet of sea level rise by the end of the century, they're saying this area is looking at 3.5 to 4 feet, 4.5 feet, because of this combination of sinking and rising seas.
NOAA, of course, is the National Oceanic and Atmospheric Administration. So your project features an online map, Bob, that illustrates the extent of the crisis through time. Why did you choose to make this so visual?
This is really the really new thing about this report on our coast. I've been covering this for years, for decades. But what the brilliant people at ProPublica did with their computer and graphics skills is they went back and took official U.S. Geological Survey topographical maps and then aerial photographs and satellite photographs and blended them together, going back to the 1930s and earlier. And then they could show you what actually happened as you move a slider across some of these pages. You'll see these pristine wetlands in the 1930s turn in some areas to open water. You'll watch as these canals came in and the place just opened up and fell apart. And, you know, writers hate to hear this. I can tell you I've been working on this for decades, and people who have been reading my stories for decades say, this is the best thing you've ever done. Well, the words are pretty much the same, but the pictures, these graphics, really finally hit home as you watch this part of the state drown.
So what's been the impact of all this land loss on people living along the Gulf?
Well, there are communities now that are faced with having to move, and people are kind of angry and they're stunned, and they want someone to pay to keep their communities where they are, and the cost is just too high. So some communities are facing facts. They're saying we have to move. Others are hoping that the state or the federal government or someone will come to their rescue and build, higher, taller levees to protect them. But this could be the largest forced migration for environmental reasons in the history of the country.
Bob, in your piece, you highlight a couple of places that are particularly impacted by all of this. Tell me about Delacroix, please.
Well, Delacroix Island is a settlement about 30 miles from the French Quarter here in New Orleans that was founded back in the late 1700s, early 1800s. It's unique because it's Spanish. Back in the 1780s, when Spain owned this part of the world, King Philip was eager to have more settlers here. So he looked for volunteers from the Canary Islands. They moved here. They worked originally on plantations closer to the city, and then they moved down the bayous onto the delta. The people lived there for a couple of hundred years, and really into the 1950s, late 50s, they had very little contact with New Orleans. They had a subsistence lifestyle. They were fishermen, trappers. They picked moss to sell to furniture makers, Spanish moss. But the canal dredging that started in the 30s and 40s began to have an impact. They began noticing that the marshes, the wetlands they trapped, were falling apart, that the lagoons and the bayous were getting wider, the lakes were getting bigger. When they went to set their traps for muskrat, nutria, and mink, the traps were deeper in the water. And eventually, the storms that came through basically made it impossible for them to live full time. So the whole ecosystem, this incredible delta that not only isolated them and kept their culture unique, but also provided their living, was being destroyed. That whole culture is gone. You know, there are maybe 10 families living there now. And the amount of land that once was so high and wide that bison and elk roamed it, is now about 50 yards wide on either side of the bayou. And the rest is either wetlands or open water.
So, Bob, how aware are Louisianans living in other parts of the state of these issues, do you think?
I think they're, more aware than the rest of the country. There's been a lot of media coverage here over the last, especially since Katrina. But I think the state really just lived in denial, in large measure because one of the major causes of land loss is the oil and gas industry.
So to what extent has oil and gas, that business, been held accountable for what's happened?
Well, they really haven't. According to many studies, the oil and gas industry is responsible for anywhere between 36 to 60% of the loss. There were permits they had to get beginning in 1972 with the Clean Water Act, and the state has its own permits, but they really were not forced to comply by the permits, which required them to return the areas they were working in pretty much back to their original state. So instead of backfilling these canals when they were finished, that was not done. A lot of the waste pits that are out there were not properly taken care of. In many cases, oil companies, when they well ran dry, just left the damage there. There was a landmark lawsuit brought last year by the local Flood Protection Authority seeking damages from 97 oil, gas, and pipeline companies for wetlands loss. They're saying that without these wetlands, storm surge is higher. It's going to cost us more to keep the city in this area safe. But that provoked the ire of the state's political establishment, including the governor, who promised to get the legislature to pass laws retroactively preventing this board from suing. And they did get one through, and that's now in federal court on a constitutionality test, and we'll find out what happens there. So they really have not been held accountable for the damage done.
Bob Marshall is a reporter with a lens. Thanks for taking the time with us today.
Thank you for having me.
And you can find a link to his report at our website, loe.org.
So I'm not sure if you noticed, but the very last spot that I zoomed into is the Chapalaya River Delta, and it's actually kind of a success story. So these areas have naturally built about 18 square miles of new land in the past 40 years, and that's because resource managers have managed the freshwater inflow in this area, allowing for natural sedimentation. So that is all I have for you for aquatics. Thanks so much for having me.
Okay, that was sad. It's amazing how we can change our environment. So if you have any questions for Dr. Oakley, she had her email up at the beginning. She'll be happy to answer questions.